Dois, três, teste, som, som.
Can you speak something to
Hello.
say
Test.
your name?
I'm Bruno. Hello.
Say sure.
Hello. This is going to present the work. Oh.
You have microphone.
Microphone?
Right?
Yep.
And if there are questions, we use this and we can leave it on. It's already on. Perfect. Okay. Okay, great. So let's get started. So we have half an hour, then 10, 15 minutes a break so that we can change room if we want, and then another half an hour. And we have Bruno starting with 5-point functions.
All right. Thanks. Thank you for choosing 4-1 today, or for this talk anyway. And thank you to the organizers for the upgrade. So today I'll be telling you about a paper that came out last week with my PhD supervisor Vasco, as well as João and Alice, who are in the audience, and also Zongjie and Yichao. And this work is about correlation functions in n equals 4 super Young mills. Can you see this? And as usual, we work in the planar limit. And furthermore, we'll be focusing on the strong coupling limit, where the 't Hooft coupling is very large. And in this limit, this theory is dual via the ADS-CFT correspondence to 3-level supergravity in an ADS5 cross S5 background. And on the n equals 4 side, we'll be focusing on these single trace operators. Known as half PPS operators, which are dual in the bulk to Kaluza-Klein modes of supergravitons. And one interesting thing about these correlators, about these operators, is that they are protected. This means that their conformal dimensions don't receive any quantum corrections, and in particular, for these operators, their dimension will be exactly equal to p for all values of the coupling. And we want to consider correlation functions of these operators, and I'll be using this notation. So, in terms of these correlators at 4 points, the story has pretty much been told. This is known that for arbitrary values of these p's, in particular, the ultimate form was derived by Leonardo and Shinan in 2016. But for higher points, the status isn't so good. In particular, at 5 points, the most general object that is known is some configuration of KK modes pp222, where p is any value. And this was computed by Vasco and others, where so 2023, where among these others are also João and Shinan. But there are many reasons that we should care about extending the status and about higher points in general. One such reason, so let me, why higher points? One reason, as Francesco mentioned last week, is the ADS unitarity method. So this is a method by which, if you have some loop diagram in ADS, you can perform what is called a unitarity cut. And for example, this allows you to obtain like a 4.1 loop diagram by cutting, and then you glue together two 4.3 level diagrams. But if you start considering higher loops, like 2 loops. At this point already, the cut gives you to 5.3 level diagrams. And so if you want to play these unitarity games, at some point you need to start including higher points. Another reason that we care is that there is new CFT data that is hiding in higher point functions. And this is because typically when we consider correlation functions, we want to keep our external operators nice and tidy. We like to consider typically external identical scalars, for example. And this is not only because we don't like to carry inconvenient tensor structures around, but also because to apply stuff like crossing and use the bootstrap equation, we need identical operators. But this also means that we're missing some of the CFT data, because identical operators means we can only exchange symmetric tensors in the OP, and so clearly our analysis won't be sensitive to some data. So if you want to include this, then we should either generalize the external operators that we use, or we should go to higher points so that these more general operators will appear as intermediate states. One final motivation, which will be very relevant for our work, is this observation in the 4-point function of the hidden 10D symmetry. And one can see this as follows. So first, we can define a so-called master operator by summing this operator OP over all KK modes. And then we can consider correlators of these operators, which I will just denote as Gn. And this, of course, is just equal to summing the correlation function of specific KK modes over all possible configurations of PI. So in this way, this function Gn sort of acts as a generating function for each of these. You can take this, expand in the y's, collect the terms which have the correct powers that you care about, and then you recover a specific one of these correlators. And this 10D hidden symmetry can be seen in the fact that this the generating function at 4 points, G4, has this decomposition where you pull out the tree-level part, and the remainder can be written as this function R, which is a superconformal invariant, times a so-called reduced correlator, which is only a function of the combination xij squared minus yij squared. And this is a 10-dimensional distance, which I'm going to call x hat. And this is what is called the 10D hidden symmetry. So now it's natural to wonder whether this is a feature, this is an accident, happy accident at 4 points, or if this is a more general feature of the model and it generalizes to higher points. So an obvious next target is the generating function G5. And this will be our main player in this work. Okay.
Sorry,
yeah.
Is this hidden symmetry expanded of only tree-level supergravity or beyond that?
So this is derived from tree-level supergravity. Yes.
But is it expected to hold beyond that?
It is not, not that I know. There is no hint that it's expected to hold beyond that. No.
Okay, no, thank you.
I keep it past the next.
Sorry, so it's a 10D symmetry, but what is the symmetry group?
The symmetry group, this is not a symmetry in the traditional Lie group sense. It's maybe a more appropriate name would be hidden 10D structure.
Well, but this 4-point function seems to be, invariant under at least Poincare.
Sorry?
Well, what you wrote, this H4 seems to be invariant at least under Poincare, right? In 10D.
Yes. So, okay, so that function is invariant under the 10D conformal group. But, okay. We're not at the level where we can formulate this that precisely, I suppose. It's still a bit mysterious, but in terms of that function, at least it's Lorentz invariant, and 10D Lorentz. That's
Okay, but
yeah, conformal.
But when you're hoping for to see 10D symmetry in higher point correlators, what does it mean? Are you hoping that like X and Y will combine in some nice way, or are you hoping that there's actually going to be some symmetry?
So So the precise statement is that we expect to have some sort of decomposition like this. In general, there will be more superconformal invariants, so we hope to extract some tree-level part, and then generically a sum over some invariants times some reduced correlators, where these will only be a function of this 10D distance.
And so they're going to be 10D conformal invariant.
Yes.
So the answer to my question is it's conformal group.
Yes.
Okay.
Yes. Okay.
H.
Okay. So.
Whole thing, sorry. Maybe
Yes.
The whole thing is not invariant. It's only this funny reduced H, which will have this somewhat mysterious 10-dimensional conformal symmetry.
Thanks. Okay, so traditionally, when we're faced with these holographic correlators, a nice representation to use, a nice tool, is the Mellin transform. And this is defined in this way. So let's say you have some correlator of KK modes, and you can write this as an integral of some function n times some other stuff. Where this m is called the Mellin amplitude, and these gammas are called the Mellin variables, and they obey this restriction.
Sorry, Bruno, I don't mean to derail you, but I think you can assume that everyone here knows what Mellin amplitudes are and knows the 4-point function story. Otherwise,
Sure.
no one would come to a 5-point talk.
Sure. Okay. Well, okay. So I wanted to write this anyway. So I won't give any more detail. But this is the ordinary Mellin transform. The problem with this is that for our purposes, we're studying symmetry, which combines x and y into this 10-dimensional object, and the Mellin transform breaks that symmetry because we're treating x as being explicitly different from y. And so in practice, we want to do something to maintain this symmetry, a representation which maintains this symmetry, and this leads us to consider the so-called ADS cross S transform, which is essentially the same thing, except you do an analogous transform, a Mellin transform in the y variables, which is going to be discrete. It's going to be a sum instead of an integral. So maybe I can skip over a bit and just give you the ADS cross S transform. So we'll be using this formalism, which is the so-called ADS cross S Mellin transform. This was introduced by Pedro and Francesco. And it's a useful formalism for our case because now we're treating them as the two kinds of variables as being equal. Okay. And so when you consider a specific KK mode, so the Mellin variables will obey the usual restriction, and so will the n's. So these n's will obey the same restriction as the usual Mellin variables. But the great thing about this formalism is that it allows us to treat directly the generating function, to work directly at the level of the generating function. And we do that by summing over all pi's here. So we obtain just the generating function gn. And then effectively what this does is you remove this restriction on the nij's. It's no longer equal to pi, because you sum over all pi's. And then the only restriction is on the integration variables, which are fixed to be equal to nij, to the sum of nij's. Okay. And now the statement of hidden symmetry is by looking at the 4-point amplitude of the generating function, it can be obtained as some difference operator r hat, which is obtained by promoting the superconformal invariant r to a difference operator. and then it's acting on a reduced amplitude M4 tilde, which is only a function of gamma ij minus nij, and these variables I'm going to call rho ij. So this is how the hidden 10D symmetry manifests at the level of the ADS cross S amplitude. Okay. Now, one nice property of the Mellin transform that is useful and we want to keep is that there's this the factorization property, and we're wondering we might wonder if we can make an analogous statement at the level of this ADS cross S amplitude, if there's a sort of ADS cross S factorization. So typically, you have some endpoint function, you take some OPEs, you exchange some operator X here. And this corresponds to a series of poles whose residues can be obtained by gluing together the left blob and the right blob's Mellin amplitudes. And now, can we extend this to a formalism at the level of the generating functions? And in fact, we can. The key point is that this property of factorization is a consequence of the Casimir equation. You apply the Casimir equation and you focus on a specific set of poles. Now, if you look at our symmetry isometry group of ADS cross S, this is the group, ADS5 cross S5, where this is the conformal piece, or ADS5 piece, and this is the R symmetry, or spherical piece. But these groups are very closely related. In particular, they're Wick rotations of each other. And so their Casimir equations and their solutions will be just obtained by Wick rotating from the conformal group. So from this group will be obtained from this Casimir equation by Wick rotating. And this allows us to use the same argument that was used in the factorization of Mellin amplitudes paper by Vasco, João, and Emilio. And just the same argument follows, but we Wick rotate everything. And essentially what happens is that we do some relabeling, where the quantum numbers delta and j and the Mellin variables gamma will be replaced by minus r, s, and minus n, where these r and s are quantum numbers which define the SO6 representation. This we call the sphere dimension, and this we call the sphere spin. And these are related to the SU4 Dinkin labels, which is the same as the SO6 is isomorphic to SU4, so typically people do this identify in terms of the SU4 Dinkin labels, but they're related to those labels in this way. Okay, so now we have a factorization formula for SO6, and now we can combine it with the ordinary Mellin factorization to obtain a sort of ADS cross S factorization formula. Okay, so how am I doing on time? Okay. So now with this factorization, we're in a position where we can reconstruct the generating function, or the amplitude of the generating function M5, by looking at the Mellin amplitudes, or the ADS cross S amplitudes of the descendants of 4-point functions where one operator is one of the descendants that's exchanged here in the middle. And fortunately, in the strong coupling limit, all single trace operators that are unprotected acquire large conformal dimensions and decouple. And so the only operators that we need to consider here for X are the protected ones, which are in the happy PS superconformal multiplet. So you act with these supercharges, and you obtain all which are the same ones in that table over there. And these are all to consider. And in particular, they're all super descendants of the superconformal primary O. And this means that we can obtain this 4-point function schematically as acting with some supercharges on this 4-point function of O's, which we know. So, and this can be implemented in Mathematica, but unfortunately it's a bit easier said than done. And in particular, at least our implementation scales quite badly with the level of the descendant, and we were only able to act with these up to level 2. So in practice, what we obtained is the functions with J, T, and O, and A, sorry. O, of course, we already knew. Of course, we can't just directly glue them together using the factorization unless we know all the descendant amplitudes. So what can we do? Well, okay, we're at the Bootstrap conference, so we might ask if we can bootstrap this correlation function, if we can find some pattern in these descendant amplitudes that allows us to impose some properties directly at the level of M5 and just determine it. So one property that we notice is that these descendant amplitudes only have poles in rho. And furthermore, through the factorization formula, they are glued together with 3-point functions in such a way that their contribution to the 5-point amplitude also only contains poles in rho. And another thing that we notice is this remarkable so-called Z2 symmetry. And that is easily seen by looking at the quantum numbers of these operators. So if you do this replacement that is given to us by the Wick rotation, and additionally change P to minus P, then, so these operators O, J, C, and F are invariant under this symmetry, while T and A are exchanged. And this is exactly what we see at the level of the Mellin amplitudes. So if we apply this Z2 symmetry, then the Mellin amplitude for J is sent to minus Mj, and the amplitude for T is sent to the amplitude for A. This relative minus sign here is just a consequence of our normalization. Okay, so we really do observe this symmetry, and now we might wonder if how strong is it? If we want to impose this at the level of the generating function, how far can we get? Okay. So now let's move on to the bootstrap section. This symmetry, yes. Yeah. Okay, so we can set up a bootstrap problem. So we're looking for a function M5, and we demand certain properties for it. Firstly, we want it to be meromorphic with poles in rho at positions of single traces.
So this is a bit of an assumption, right? Because you didn't check it for the two last.
Yes, exactly. Yeah. We also demand that it's crossing symmetric. Okay, this is not an assumption because we just consider a 5-point function of identical operators, which are these master operators. And also, we impose the Z2 symmetry. Okay, and actually by imposing just these 3 conditions, we're able to fix the entire singular part of M5. So M5 is a meromorphic function, so it's going to have some poles, and then the regular part, the entire part of the poles is fixed by this procedure. Of course, the Mellin amplitude or the ADS cross S amplitude doesn't just have poles, it has a regular piece. And to fix that regular piece, we impose a further condition from supersymmetry, known as the Drucker-Polevka twist. Which at the level of the amplitude is simply given by a difference operator acting on the amplitude gives 0. And this difference operator will mix the singular and regular pieces and allows us to fix the regular part. So at the end of the day, we are able to uniquely bootstrap the ADS cross S amplitude M5.
Sorry, can you say a little bit more about this Z2 symmetry? Is it a subgroup of the bonus symmetry of supergravity?
Of the
This
yeah.
this U1 that under which Q and Q tilde are oppositely charged, which is not a symmetry of string theory, but it is a symmetry of three-level supergravity.
Yeah, I'm not entirely sure. So this is a symmetry that is observed at the level of those descendant amplitudes for sure, and
So it's okay. So you're exchanging the two. So it's not that, but
yeah. So it sends p to minus p. So this is really only observed at the level of the generating function. You need to sum over all p's.
Super nice. So singular part means terms with posing two variables at the same time and pose with
Both. So both in two variables at the same time and just one pole.
thanks.
Yeah. Okay. So we were able to fix this uniquely, but importantly, we didn't actually use any of the dynamical information, well, hardly any, from the 4-point functions that we computed by explicitly acting with the supercharges. We have some input in the form of where the poles should be, but
Sorry, what is this Z2 symmetry?
so, okay, this can be seen as an assumption that we observed for the 4-point functions that we computed explicitly, and we expect to hold more generically because this symmetry can be seen at the level of the quantum numbers of the operators.
Yeah, that was not an answer, yeah. What is this Z2 symmetry? If it's a conjecture, I don't care, but what is it? What is the conjecture that it corresponds to?
So, okay, so there is some, we can decompose this function in terms of in exchanged operators, and they're going to have some quantum numbers of the conformal group and of the R symmetry group.
Right, and P is some integer, right? 2,
Yes.
3, 4, 5, there's no minus 5.
There's no minus 5, no.
Okay.
So, but
Now you're doing some P to minus P, I'm a bit not sure.
can you write a little bit more clearly? It's a bit hard to see. What are you saying? You're sending M? What?
So Mj is the ADS cross S amplitude of the correlator with J. So this is Mj.
Maybe you need a different pen.
Can you throw away this one, please?
Sorry?
Can you throw away this one, please?
Oh, okay.
On that speakers.
Yeah. So Mj goes to minus Mj, and Mt goes to Ma.
Under what? What did you do to MJ to flip it?
So we did this exchange, and then also P to minus P.
So this function, it's not O2, O2, O2J, it's something different?
No, this is OOOJ, where O is the master operator, and J is the analogous for the descendant. So for each OP, you act with the supercharge, you get JP, and then you can sum over all P's to get this master operator J. And then this gives you, you can have an ADS cross S amplitude for this function of master operators.
Sorry, but P, I thought P was a positive integer.
Yes, it is.
So you're saying that if in the function M of P, you flip P to minus P in that function, not in the sum, but in that function, then M flips sign. Is that the statement?
So,
But it's important to swap gamma and n, right?
yeah.
Those ones.
Important.
So, okay, so if you remember, the original condition was that the sum of n's equals p. So if you want to flip the sign of m, you have to flip the sign of p.
Why would I want to flip signs of anything? What is the symmetry again? I think
So this is a
maybe I don't understand.
this is how you obtain the SO6 group by weak rotating SO4, 2.
I thought that was okay. That's about what is SO6. But this
Yes.
Z2 symmetry is supposed to do something. Is it? What does this? How does Z2 act?
Well, it acts, so this is a concrete transformation, right? It acts by doing this. Now you can ask about the nature of this symmetry, and that's less clear. I agree.
So for the linearity function is have like some tensor symmetry, and this two symmetry exchanges two subgroups of this tensor symmetry, right?
Yeah. Yes.
Oh, so this arrow should have two signs, right? Delta blah goes to that.
Yes.
R blah goes
Oh, yes, sorry.
But the symmetry does not live invariant the measure, right? The gamma functions won't be. They just have M. Maybe that's the confusion.
Yeah, yes, exactly. So this acts at the level of the amplitude and not in the measure.
that.
Okay, so I'm probably running out of time, or have run out of time. But just to mention, okay, so we bootstrap this amplitude, and in principle, this should contain information about infinitely many correlators of KK modes, as well as infinitely many descendants. And so this is, quite a strong claim, because these are still assumptions. And so we need to check whether our result is correct. And we gave some pretty strong checks. So one check that we can do is by checking against the 4-point function that we explicitly computed. And importantly, this was not an input to our bootstrap. So we computed these 4-point functions explicitly, but we didn't use them to fix any of the coefficients here. So we can look at our bootstrapped M5, use our factorization formula to extract the 4-point functions, and then compare it to the explicit ones, and we obtain a match. We can also check specific correlators of KK modes that we extract from our bootstrapped amplitude against the explicitly computed results that were available before of PP222, and we also obtain a match. We can also impose an independent supersymmetry condition from the Duker-Plewka twist, which is known as the chiral algebra twist. Okay, this is just some supersymmetry condition, and we also verify this. Another check that we can do is to extract some double trace correlators where this one external operator is multi-trace instead of just a single trace. And for all cases that were extracted, the result checked out. Okay, so we made some assumptions and we bootstrapped an amplitude, and it passed some quite non-trivial checks. So at this point, we're pretty happy with the result, but we're still one step away from doing the decomposition that I wrote here for this ultimate form, which would be writing our amplitude as some sum of difference operators derived from supersymmetric invariants acting on reduced amplitudes, which are only functions of rho. And we were able to do this just by brute force, by listing all possible supersymmetric invariants and then trying to write something of this form. But unfortunately, I have to end on a sour note that this decomposition that we found is not unique. So there's still some degrees of freedom that we were not able to fix just by comparing with some ansatz. And so, yeah, so that's the status at this point. So how's the time?
It's over, yeah.
Yeah, okay. So maybe I'll just say some words about future directions. So, okay, so the order 0 future direction would be to fix these remaining coefficients. There is some notion about how to do this by moving to position space, some specific correlator of KK modes, and then that correlator can be written as a sum of D functions, and we know which ones should appear and which should not. And this allows us to fix some coefficients, but we weren't able to fix all of them yet. Another interesting direction that we could take this is to try to apply these conditions at higher points. In principle, none of these are too hard to implement at higher points, but of course we don't know if they will be just as restrictive for 6 points, for example. So that would be interesting. And another thing that we could consider is, okay, so we've only considered single trace external operators here, but in principle, this should contain information about infinitely many correlators with double traces. So a lot less is known about these double trace correlators, so this would be something interesting to do. And if we can also bootstrap M6, for example, then we can start including more and more double traces. But okay, this is for the future. So I'll end here. Thanks.
Questions?
It's on.
It's on, yeah.
So the assumption to have poles in row, is that assuming this 10D symmetry? Did I understand that correctly?
Yeah, so okay, so this assumption is, so this would not be an assumption if we have calculated explicitly all the 4-point functions. All the 4-point functions we observed have this property that they only have poles in row, and that they are glued together in such a way that their contribution to M5 also only has poles in row. In principle, this gluing procedure could introduce poles in gamma, just in gamma and not row. So this would be what we call spurious poles. But it's an assumption of our bootstrap that this does not happen. And so this doesn't, so this will be a weaker form of hidden symmetry. The true statement of hidden symmetry formally is that you can write like this.
Yes.
So
Why? Maybe yours is better, right?
Maybe just more comment on to this. It's actually social. To a subtlety of the ADS cross S factorization formula. Actually, if you expect there's any physical pole in a particular, say, KK correlator, then actually one can show that by summing up all the KK correlators, this pole has to be grouped with some other poles in other correlators to form into really a pole in 10 dimensions. So by that, you can argue that if for any physical pole, it has to be packaged into the row pole. So in this way, you can argue that once you've confirmed that at 4-point there's just row pole, then just by the argument of the ADS cross S factorization, you would know that in principle the 5-point doesn't have any spurious ones. Yeah, so there's roughly the argument for why we can make this assumption.
okay, thanks.
So I was wondering, this Z2 symmetry is basically sending the radius to I times the radius, right?
Yeah. So okay. So what? Which radius? do you mean?
I mean, of
ADS?
ADS. Yeah.
So yeah.
Yeah.
Yeah. Yes.
Yeah.
It's
I think it's like a symmetry of the Green-Schwarz action of the string. Probably it even holds to all other perturbing alpha prime.
Oh,
Anyway.
maybe
It's true.
We can ask more questions during the short break. So let's thank Bruno again. So the next talk here is in 8 minutes, 6, 7 minutes.
Away, so I guess I can be one. Yeah, welcome Alessandro with his talk on bootstrapping the simplest deconfined quantum critical point.
Okay. Thank you for coming, and thank you. Thank the organizer for organizing this conference and giving me the opportunity to speak. So today I will talk about a work that I did in collaboration with Shai, Martin, and Ning that appeared last month, in which we are trying to give some evidence using the numerical conformal bootstrap about the existence of the confined quantum criticality. So I will start with some motivation of why we are doing this, and I will try to attempt at doing a recap of what is known about these theories and what is the data against which we can compare. Then I will discuss a very simple bound on O2 symmetric conformal field theories in 3 dimensions that led us to devise a strategy to try to focus on these kind of critical points. And then I will discuss the results and finally some future directions. So very broadly, as you know, gauge theories in 3D, especially when coupled to matter, can exhibit a wide variety of phases in the IR. But the dynamics is typically strongly coupled, so it's often hard, unless we are like in supersymmetric theories, to make precise statements. And in particular, since we are at the Bootstrap conference, we are interested in conformal phases of these gauge theories. And one hope is that maybe with the Bootstrap we might be able to say something about the non-perturbative physics. But unfortunately, so far, the progress in this direction has not been so good as has been for in case of like multiscalar theories like Ising model, the ON models, or Grosnev-Yukawa universality graphs. So I tried to collect here a series of papers in the past year that worked on this, especially on abelian gauge theories, but okay, as I said, so far we are still probably a bit far to the goal of isolating these theories, these CFTs in theory space. Another interesting take comes from more from a condensed matter perspective. These are the so-called confined quantum critical points. So almost 20 years ago, it was proposed that there is a class of 2+1 dimensional lattice models that exhibit quantum phase transitions that go beyond the ordinary Landau paradigm. And in particular, in this talk, I will focus on the so-called Néel valence bond solid transition in SUN quantum antiferromagnets. So this is a transition between 2 phases that preserve 2 different kind of global symmetries that we call H and H prime. In the case where these global symmetries are not a subgroup of one another, a continuous transition is usually disallowed in the Landau framework. But okay, from lattice simulations, the actual nature of this transition is still debated up to date. But okay, in any case, the lore, in some sense, is that the critical dynamics should be captured by a field theory of gauge fields coupled to matter fields. So these phase transitions are dubbed deconfined in the sense that the gauge degrees of freedom emerge only at the critical point. So the prototypical example of this kind of theories is quantum electrodynamics in 3 dimensions coupled to either n bosons or n fermions. And in this case, you can think of one symmetry group of being the flavor symmetry of the matter fields, while the other symmetry group is the U1 topological symmetry that is present in 3 dimensions for abelian gauge fields, and whose charge operators are so-called monopoles. So one can generically show that at large n, the theory flows to a conformal field theory, but there is a question of what happens at small n when the theory is strongly coupled. So let's go to the first values of n that are possible in parity invariant theories. So for the n equal to 1 theory with 1 boson is conjectured since a long time to be dual to the O2 Wilson-Fisher CFT. The n equal to 2 theory with the theory with 2 fermions was shown using the Bootstrap to be likely not conformal, while the theory with 2 bosons is was argued to be to present either a weakly first order transition in this paper, in this fuzzy sphere work from last year, or to have a multi-critical fixed point with SO5 global symmetry enhancement, and this was argued either using the Bootstrap in this work by Shai and Ning from last year, or later with there was also like some further evidence from the lattice corroborating this picture. So this leaves, in some sense, the n equal to 3 bosonic theory to be the simplest putative example of the confined quantum criticality, so in the sense of only one relevant singlet.
Do you have time to remind us what's wrong with n equal to fermionic theory?
So here, likely non-conformal. So I think the issue was that there is a conjecture. I mean, this is a bit conjecture over conjecture in some sense. So there is the conjecture that the n equal to 2 fermionic theory is supposed to enhance to a larger global symmetry in the AR, I think, O4. But it was, I think, shown that assuming only one relevant singlet under O4, then the Bootstrap puts like some bounds that exclude the lattice data from this kind of theories, I think. So, okay, so now I will try to summarize what is known about this theory, starting from the lattice, where I said the situation is a bit is still debated. So recently there were simulations, Monte Carlo simulations of the lattice abelian Higgs model. So this is like the naive discretization of the continuum QED theory with n scalars on the lattice. And in this work, it was shown that this kind of lattice model with 10 of these scalar fields has a second order phase transition, while the theory with 4 scalars has a weakly first order transition. So if you believe that there is some kind of conformal window, then this would imply that the n equal to 3 theory also is not conformal, but okay, the simulation was not done explicitly for the n equal to 3 case. On the other hand, as I mentioned before, there is quite a series of work about these Nel VBS transition in SUN quantum antiferromagnets, which suggests instead there is a second order phase transition for n greater than 3. So from this work, we have prediction for the simplest critical exponent that one can measure in this system, which correspond to scaling dimension of the lowest lying singlet, the lowest lying scalar in the adjoint of SUN, and the lowest lying monopole operators. But I must say that not all the critical exponents from across different works are always compatible with each other. So as you can see, the situation from the lattice is a bit murky. So let's now go instead to field theory. One approach is the epsilon expansion. So you write down the renormalizable Lagrangian in 4 dimensions for a gauge field, abelian gauge field coupled to n scalar fields in the fundamental representation of SUN. And this is the Lagrangian of scalar QED that I will call also the same. I mean, it's also known in some literature as the CPN-1 model. So if you tune the mass to 0, oh, something happens. The cursor is not. Try again. Oh.
The internet's full.
Ah, okay.
Share again.
Okay. So if we tune the mass to 0, then in for minus epsilon dimension, we have a qualitative picture of a conformal window. So for minus epsilon expansion gives qualitatively a value of n and star such that for n greater than n star, we have only one stable fixed point. It's this point here for a finite value of the coupling lambda and E squared. While for n smaller than n star, we don't have any stable fixed point, so this will predict generically first order transition. But the quantitative extrapolation to epsilon to 1 is problematic in the sense that the loop corrections that have been computed in the past have large coefficients as compared to, for instance, Wilson-Fisher CFT. So this makes the extrapolation to epsilon to 1 difficult because the results depend quite a lot on the loop order that you take and on the different kind of summation that you try to do. So, for instance, with the one loop beta function, it would predict a value of n star around 180, so very big. But okay, if you start using the 5 loop results, this goes down, naive extrapolation, this goes down to 70. Then people try to do some kind of interpolation with some other results in 2 plus epsilon dimension, and they interpolated this value down to 12 plus or minus 4. So as you can see, this also from the epsilon expansion, we are a bit in the dark. So another computational approach is large n, as I said before. So at large n, you introduce your usual Abbarsan-Antonovich field, sigma, and in 3 dimension, you drop irrelevant terms, and you tune the mass to 0. In this case, what you obtain at large n is the action of a nonlinear sigma model with CPN minus 1 target space. And perturbatively, you can build operators in this CFT from the fundamental fields in the Lagrangian. And these fields will be either singlets or charged under SUN. And there is only one relevant singlet, which is this sigma field, which at large n has dimension 2 plus 1 over n correction. And scaling dimensions in this theory can be computed at leading at subleading order in 1 over n, but also here the extrapolation to small values of n is problematic, especially for the lowest laying field, in the sense that you typically get values that are below the unitarity bound. However, there is a more successful story, which is the computation of scaling dimensions of monopole operators at large n. So monopole operators are not fields that are naively built out of the fundamental fields in the Lagrangian, but they are instead defined as local insertion of quantized units of flux for f mu nu. And their scaling dimension in the CFT can be, at large n, can be identified with the ground state energies of the CFT on R times S2 with some fixed unit of magnetic flux, which is related to the charge of the monopole under U1. And the scaling dimension has been computed to leading and subleading order in 1 over n in this very nice paper from 2015. Silvio was one of the authors. And one striking fact about this computation is that there is actually a very good match, even at small values of n, with the critical exponents of this Nel VBS transition. So here is the picture I took from that paper. So where we compare with this oblique line is the large n expansion to leading and subleading order of charge 1 monopole operators. So the lowest lying scalar in that sector, while the dots are the scaling dimension that you can extract from the critical exponent of the VBS order parameter in these SUN antiferromagnets. And as you can see, for being like a large n expansion to the just leading and subleading order, the match is quite remarkable even at small values of n. So before proceeding, let me just write here, because it will be important later, what is the full global symmetry of this theory. So we have you have an SUN global symmetry. Then, okay, if you want to be more precise, this is a gauge theory, so you have to quotient by the center of SUN. Then there is the U1 topological symmetry. And then there is also charge conjugation symmetry, which puts this further Z2. So this will be the full global symmetry of the theory.
Take
yeah.
a mic, please. Can you say a bit more what is different, this comparison for monopoles as opposed to other operators? What would this plot look like? Why monopoles agree better? Is it because they correct 1/n corrections are smaller than for the other operators?
I think the point is that 1/n correction are smaller for monopoles than for like meson fields that you built out from the Lagrangian. But okay, we don't have a lot of orders to compare with, so it's more like an observation.
But is there some attempt to understand why the monopoles are less subject to 1/n corrections?
Well, I would be interested in understanding it. I don't know if someone else is trying to do this, but I don't know if Silvio has any. Okay. Okay. So another computational scheme that we will be useful to compare with is the large charge effective theory. So this will be useful when comparing to operators that are only charged under these U1, so monopole operators. So as you might probably know, the large charge sectors of U1 symmetric conformal field theories is captured by a universal effective theory in which you can compute scaling dimension of operators of the lowest lying primaries as a power series in the charge. And so this is the first order prediction for the scaling dimensions from the EFT. So there are two coefficients, C3 and C1 which are theory dependent and are the effectively the Wilson coefficients of the effective theory, while there is instead a universal contribution here, which is the Casimir energy of the effective theory. And in the case of the CPN-1 model, these coefficients were fixed at large n by comparing this large charge formula with the large n expansion that can be done for arbitrary values of the charge. And another nice feature of this EFT is that it also predicts scaling dimensions of spinning operators of charge Q. So exactly in the sense of EFT, once you fix these two coefficients, say with the spin 0 data, then the EFT predicts what are the scaling dimensions of spinning operators thanks to this universal spin-dependent term. And so in principle, this EFT is valid in a regime of very large charge, and the spinning formula is valid in a regime for very small spin compared to the charge. So it turns out that the regime of validity seems to be much larger than what one would naively expect. And as a benchmark, we compare these results in the critical with the critical O2 model. So in the critical O2 model, these coefficients, these Wilson coefficients, were fixed with Monte Carlo simulations for the spin 0 scaling dimensions. And so once we know this data, we can extract the scaling dimension of spinning, predict from the EFT, scaling dimension of spinning operators. And here I'm comparing instead, so the large charge predictions with the instead the determinations of these scaling dimensions from the Bootstrap. So this is either from the Precision Islands from 2020 or this later work where they did the EFM computation of the spectrum of this theory. And as you can see, so for spin 0, the agreement is quite remarkable even to very small charges. This was in some sense already known previously. So what the new observation is that actually the formula for spinning operators also agrees in the whole range where the spin is less than the charge. While for spin larger than the charge, this EFT formula typically predicts scaling dimensions that are below the unitarity bound. Okay, so let's now go back to the Bootstrap and So in our work, we focus just on the sector of operators that are charged only under this U1 symmetry. So we'll not explore the full global symmetry of the theory, but only this part. So U1 topological times Z2, which makes NO2 global symmetry. So the first thing is to study the space of conformal field theories in 3 dimensions with O2 global symmetry. And one of the simplest setups that you can consider is the mixed correlator system of scalar primaries of charge 0 and 1. And is the same setup that was used in 2015 to obtain the first islands for the O2 model. And if we assume that these charge 0 and charge 1 operator are the only relevant scalar primaries in their charge sectors, we can bound the scaling dimensions delta 0, delta 1, and the ratio of OP coefficients. So this is the plot that one obtains, which is some kind of extension of the plot that was done in this paper. So in this space, CFT space, we have a very tiny island, which is the one of the critical O2 model. And then to the right, there is a huge continent of a lot of scaling dimensions that are not ruled out by the bootstrap, at least with this assumption and given derivative order, or given order in the derivative functionals. And it's interesting now to see where the predictions for the scaling dimensions of this nil VBS transition sit in this space. And so here in green there is the estimate from the lattice for SU3 antiferromagnets. So let me write maybe here. So CP2 is SU3 antiferromagnet. CP3 is SU4 antiferromagnet. CP4 is SU5 antiferromagnets. And while instead these dashed vertical lines are the large N prediction for the charge 1 monopole operators extrapolated at finite values of N. So we have N equal to 1, N equal to 2, N equal to 3, N equal to 4, N equal to 5, and so on. So one...
Why are the 2 yellow ones? Is it the determination is not bad for CP4?
Yeah.
Okay.
So yeah, I mean the error bar is very big, but at least in like delta 1 direction the two are compatible, while in delta 0 direction there is no estimate of the error bar, so we don't know. And also here, so this dot is still from the lattice, but there is no estimate for the error bars, where the green box means that there is an estimate for the error bar.
So delta 1 grows with N and delta 0 is constant with N.
You're supposed to use
Yeah.
the mic.
Yeah. So the question is that, the observation is that as we go to larger values delta 1, which correspond to larger N, delta 0 goes to 1. Yeah, so I guess your comment was that at large N you would expect it to go to 2. I don't know.
Well, so each vertical dash is one value for N.
Yeah.
So that means delta 0 is constant at large N.
Yeah, from this bound.
And delta 1, this is not a bound, this is just the plot, right?
It's not a bound in which sense?
These vertical dash things, they're not a bound, no?
No, they're just the value from large N.
Yeah.
Okay. He's just not including at all the prediction for the singlet because this is from large N because it's not accurate at all. This series has larger.
Okay.
Yeah, the line for large N, like it starts very below here, it goes up, and then at some point from here on it starts intersecting this, and eventually goes to 2.
Okay, thanks.
Yeah. Okay. So this led us to, so the observation that we made is that, so this lattice data almost intersects the allowed region from this bootstrap. So this can lead us to start to make a conjecture that then we try to test so the conjecture is that the CP2 model is critical and is approximately an extremal CFT in this space of scaling dimensions. So it sits almost here at this boundary point. And however, since there is no sharp feature at this point of the boundary, the strategy that we decided to use was to, in some sense, trust the large n estimate for the dimension of delta 1. So this will be like an input to the bootstrap. We fix that dimension. And then to go to the boundary point, we minimize delta 0. So maybe this seems a bit out of the blue as a strategy, but the whole point is to try to see if this conjecture is true or not. And then, okay, eventually, I mean, from our point of view, we have gathered enough evidence that this might be actually correct. Then what the system that we consider is the mixed correlator system of charges 0, 1, and 2. So this is the same setup that led in 2020 to the O2 Precision Island. And we will assume that these are the only relevant scalar operators in the respective charge sectors. And then the bootstrap allows us to explore this 6-dimensional space of CFT data, so pre-scaling dimensions and trio-P ratios. And the strategy is to minimize delta 0 at a fixed value of delta 1 given by the large n value. And so here we look at the cross-section of this 6-dimensional space. So this is, in some sense, cutting vertically in the previous continent. And as you can see, the allowed region is centered around the value for delta 2 that comes from large n extrapolated to n equal to 3. And you can see that minimizing delta 0 in this slice correspond to some kind of corner in this CFT space. And then once we are at the boundary of this allowed region, we can extract an approximate spectrum using the extremal functional method. And this will be useful to gather more evidence that this conjecture might be true. So let me jump now to the results. So these are the results for the scalar sector that we can access with the bootstrap. So let me explain a bit this table. So in the first line, there are our bootstrap estimate. Star means that it's a value that we inject in the bootstrap. So we inject one value, and with this procedure, we extract a platter of CFT data using the EFM. Then the prediction of our estimate for these scaling dimensions have an error that is not a rigorous error of the bootstrap. It's just an estimate of the error that we decided to put because we saw that these values were, some of these values were quite dependent on the lambda parameter of the number of derivative functions that we use in the bootstrap. So what we did was to do this computation for different values of lambda in steps of 2 and then extrapolate to infinite lambda. And so this error is just some non-rigorous estimate coming from the extrapolation.
I thought Shai didn't like to do this. Now he's okay.
Sorry?
I thought Shai didn't like to do these extrapolations. Now he's okay with that.
He liked it. I liked it. You're convinced. I'm convinced.
Okay. Okay. And as you can see, then we have the large n prediction for these monopole operators and these two different results from the lattice. So as you can see, for monopoles, we have a quite good agreement with the dimensions computed at large n, extrapolated to n equals to 3, while for the singlet, we match like one of these two lattice estimates, which was the one in the previous plot that had the error bar, while the other one that has no error bar is like quite below compared to this. Okay. Instead, for spinning operator, we can compare now to this large charge EFT. And remarkably, we see exactly the same pattern of matching between large charge and the bootstrap data as in the O2 Wilson-Fisher. So as you can see, for spinning operator, these are all extracted with EFM. There is a quite good agreement with large charge for all values of spin less than the charge. Okay. So
why is there no L equals 1?
Because
why is there no L equals 1?
Formula for large charge for L equals 1 gives the dimension of a descendant. So so if we go back to, I mean, it's a bit numerology. There is no, I think, proper proof of this, but that the observation that for L equals to 1, this term is +1. And so the expectation is that for L equals to 1, this formula gives the dimension of the level 1 descendant of this primary. While for greater L, this gives some non-integer shift. And so this is supposed to be a primary.
So it's not understood how to compute spin equals 1?
Well, there is a bit of okay. I talked to one of these people doing large charge. There is a bit of understanding of how to do spin 1, but they are not sure that like these corrections are actually under control as in the same way as this. But okay.
Sounds strange. But if you just trust the formula, it doesn't match for you.
No, no, it just gives, yeah. It will give dimensions that are like this column +1, and these are much higher in the spectrum. Yeah. Okay, so let me move to conclusions. So in this work, we gathered some evidence for criticality of the CP2 model, which is supposedly the simplest putative deconfined quantum critical point. And we did so by studying the U1 sector of this theory and matching same dimension of monopole operators as well a singlet with one of two lattice papers. So a natural question now is what happens for larger values of n. So let me go back to this plot. As you can see, I mean, these lattice estimates are not very close to the boundary in this case, but nevertheless, one can try to do the same procedure. So one fixes the dimension of delta 1 to this line and then minimizes the dimension of the singlet. So in the case of n equal to 4, we actually obtain a spectrum for monopoles that has a relatively good match with the large n computation. But the dimension of the singlet does not match, as you might imagine from this plot. While for the n equal to 5 points, so this line, also some of the monopole operators don't match with the large n expansion. And for larger values of n, we don't expect this CPN model to be extremal in this plot, as you would expect at large n, the scale dimension of delta 0 to go up to 2. While this bound flattens down, and this is, okay, probably an issue with the usual fact that derivative functionals give weaker and weaker bounds at larger scale dimensions. Another direction is to try to access the SUN sector of this theory. So also because there is some kind of, there are few predictions about this adjoint operator under SUN from the lattice, so it would be nice to compare with. However, we have found, okay, we tried this actually for a couple of few months, but we found that the simplest setup, which is a mixed correlator system of singlet, SUN adjoint, charge 1, and also actually we tried also charge 2, I think, gives quite weak bounds if you make like conservative assumptions on the spectrum. And if you start playing with these assumptions, then the bounds are actually quite gap dependent. So it would be nice like either to find a different system of operators charge under SUN that gives more constraining bounds, or find some relatively trustable set of assumptions that can like make us obtain stronger bounds. So another interesting direction that we are exploring with Shai, Martin, and Ning is to maybe take more seriously this match with large charge, and so to try to set up some kind of hybrids bootstrap where you inject in the bootstrap in some way the prediction from the large charge EFT, and this would possibly lead to stronger bounds. And okay, of course, as we are bootstrapper, we always have the dream of finding islands at some point. But okay, this will probably, I think the evidence that we have up to now is encouraging in the sense that maybe we might be able to, some point, to isolate this theory, but this would require probably either more input from perturbation theory, like maybe going to higher orders in 1 over n, or some more data from the epsilon expansion, or actually more lattice data, like scaling dimensions of prediction, scaling dimension for other operators, computation larger system size, so that like maybe these disagreements go away, and so on. So with this, I conclude. Thanks.
Can I first? I already have the mic, so. So in your, so the this plot was the continent, right?
Yeah.
So I don't remember how it works for O2 setup, but if you do, say, just the easing when you have Z2, then when you consider the mixed correlator, if I remember correctly, if you don't impose some gaps, you actually don't get anything that's much different from a single correlator bound. So you don't get an island, you just get just pretty much the single correlator bound, and then but when you impose like the gap on sigma prime, epsilon prime, that they're irrelevant, then you get this island and the continent.
Yeah.
And so that if the star is the same with O2, that would make me think that the precise position of this, the boundary of the continent, it depends on some gap.
Yeah.
So my question is, what gap this depends on, and whether it depends on any gap, and if it depends on this gap, which gap it is, and if it does, so why do you think this this boundary is so special? Because if we change that gap, it would move.
Yeah, so this boundary depends mainly on the gap on the second relevant singlet. So while instead the gap on the operator after the first charge 1 doesn't move much this boundary, it starts like tilting a bit this flat direction here. And okay, so the assumption that we made was that, so that delta 0 prime 0 prime is greater than 3, which is the assumption that this model is critical.
But then on this,
yeah.
Isn't it true that the extremal spectrum on this boundary should contain this operator, just like marginal singlet?
Yeah, so actually in the FM you get an operator which is exactly at this point, and then an operator a bit higher in the spectrum, like at 4 point something.
Okay, but you don't expect in this model to be a marginal singlet.
No, but so I mean, if you start
doesn't this prove that your assumption is wrong?
No, I think that if you start increasing this bound, this will start excluding more and more the lattice points. So my take on this is that probably in this model, this second singlet is quite close to 3.
So it's close to 3.
Yeah,
I see. But how sensitive is it to this operator? Did you check this?
Yeah, so the...
like if it's 3.01, it's not going to move the thing like all the way out.
No, it moves a bit smoothly. The thing is that if you start taking it too large, then at some point you stop matching at all the monopoles in the FM. And also if you take it too small, I think there was also something weird happening in the FM. So if you take a gap which is more or less around this value, you get a good match with the monopoles. If you play around, then it stops matching at some point.
How certain are you that it's actually irrelevant? Like,
sorry?
How certain are you that it's actually irrelevant? Like,
by definition.
Sorry?
Well,
by definition, saying that it exists. How certain are we that the stable?
I mean,
yeah.
Yeah, I mean, it's okay. Maybe the bias is coming from these lattice simulations where they see a second order phase transition with just one tuning.
Well, you also told us about lattice simulations, which said that this is not conformal. So.
Yes.
Okay. Thanks.
Yeah, I was going to ask about the gap in the Q=1 sector, but maybe you said that it doesn't affect almost.
Yeah.
It doesn't affect the plot much.
No,
so maybe I won't
in this
ask.
region, it doesn't affect much. it affects this part here.
It seems unreasonable to me that the second operator in that sector would be irrelevant, because the first one is, the scaling dimension is very small.
Mm.
But if that doesn't change much,
Yeah.
the picture, then it doesn't matter.
So did I understand correctly that delta 1, we have reason to believe that large n is very good for delta 1, right? And so we fix delta 1. Yeah, so it seems to be true that delta 1 is a good thing to fix. And then we want to go to the boundary. And of course, in this section, you could do it by minimizing delta 0. But this section is a bit arbitrary, right? You could take another section of delta 1, delta 2, and go to a minimize delta 2 or whatever, right?
Yes.
So a priori, you could try maybe to go fix delta 1 and go to the boundary and pick where you go to the boundary by matching as well as possible with every data that we know, a bit like what Andrea does with this tetraquark story, where you say that here is close to the boundary, where exactly it is whatever it matches better, large Q, etc.
Yeah, I think I tested this a bit in this smaller system, not in the big, so in this two operator system, not in the bigger one. So in this case, you can try to see how much dimension of the charge 2 operator changes as you move along this boundary.
Mm-hmm.
And okay, I think, yeah, there is a bit of area around this point where you get a good match for the charge 2 operator. If you go too far away, you stop matching this.
Right, but you are still going to this boundary, right? This is not a kink, so this boundary, it's very arbitrary, right? To stay in this line. Why this particular section with delta 0, delta 1, and not delta 0 plus delta 2 over 2 and delta 1, right? I mean, it's a higher dimensional space. If there is no cusp, why would you go to a particular line in this multidimensional space? Or am I missing something basic?
Feature, but okay. If you go to the slice, you see that there is also in the other dimension a little bit of different, but yes.
Yeah, but if there is a feature in another dimension, that just highlights even more what I'm saying, right? That you should go to higher dimension. You should find where in the...
No, but if you do this slice for larger values for different values of delta 1, you still, okay, if you are, I think if you are below 1, then you slice this continent, you will still see some kind of cusp in delta 2, delta 0 space. If you take it too large, and at some point it flattens out.
Sorry, I'll ask then we'll pass the mic. So I wanted to ask a question about this continent, irrespectively of your talk. Well, a little bit respectively. So suppose that, okay, you know that there is this continent and you want to be a little bit agnostic, so presumably there are some theories living there, or you suspect that there are these CPN models maybe live in this continent. But presumably it's not just like filled uniformly with theories. I mean, there are some theories there, and at some point of the continents there are no theories.
Yeah.
Do you have, I mean, have you ever thought about like trying to understand generally, I mean, where in this continent there are theories and where there are no theories? Do you have any method in mind which would allow you to try to answer this question? Because this question seems to be even much more fundamental than just like finding some particular theory. Because eventually we would like to just decompose this continent into islands.
Yes.
So do you have any method in mind how this could be accomplished, at least in principle?
Well, yeah, I don't know much. So one thing that you can try to do is start to like play with gaps in the various sectors and see if there are points on this continent that are like relatively stable to gaps. So for instance, going a bit in this direction, so one thing that I experimented was to like try to put this gap here higher and higher, and then you will see that so until some value, this tip here of the continent is relatively stable and it closes to a sharper kick. But we don't have, up to now, we don't have like really a candidate theory for sitting there. In the same way, if you start playing with this delta 1 gap, then also this corner here starts becoming more like a tip in some sense. So I think this is some kind of like agnostic strategy maybe on trying to find theories. So you start increasing gaps in some direction, you see which points of this boundary are stable or not under this gap. So this is the idea that the direction of the idea that the CFTs are kind of discrete in this space, the spectrum is discrete, and so unless you hit some higher operator, the CFT should stay there. But okay.
Yeah, this could be an interesting thing to do.
Just very quick, I want to ask what are the gaps you used in the final search? Also, say if you use something in spin 2 or.
No, we just put gaps on scalars. So these first three that are so it's delta 1 prime greater than 3, delta 2 prime greater than 3. And then these charge 3 and charge 4. Okay, we impose that these, but this actually not like it's not. Yeah, you can actually take out this assumption, and the bound is almost the same.
But for the you put the stress tensor with fixed ratios, but then no gap above it, or
no?
Not.
We didn't do it because we don't have like an expectation, perturbative expectation of the dimension of the operator after it. So it would be a bit arbitrary.
Okay, thanks.
So about the continent again.
Yes.
So yeah, as you were saying, you played a bit with this gap, like delta 0.
Mm-hmm.
Does anything happen on the extremal spectrum when I mean, is there something a bit less continuous happening going on the boundary also when you play with this gap?
Yeah. I mean, you start at some point, if you put it too high, start seeing like some extra operator in the EFN, in the spectrum.
But I was more thinking like that for the values close to 3, like that you got. I mean, something that would give you a hint that there's something special. There's
not really. Around, if you go around 3, is relatively continuous in the spectrum. Yes.
Thanks.
Unfortunately.
Do we thank Alessandro?
talking shit about my cursive Portuguese primary school letters. Yeah, maybe. Está funcionando o microfone? Tá.
Okay, we're happy to have Antonio talking to us about an unstoppable force meets an immovable object.
Thanks. All right. Thanks, Connor. Let me start by thanking the organizers for putting together our last Simon's Bootstrap workshop and for giving me the opportunity to speak. I also wanted to add before starting that we're in a difficult time in science, and yesterday in Portugal, the Foundation for Science and Technology was dissolved. This is the Portuguese analog of the NSF or CNRS in France. And so it was replaced by some Institute for Innovation and Technology, so it's some sort of neoliberal view of science, and Lifshitz, who won the prestigious Lenin Prize, is certainly rolling in his grave, just like me. Okay, so what am I going to talk about? I'm going to talk about Lifshitz invariant fixed points. So these are fixed critical points of lattice systems, for example, that are not isotropic, so they have a preferred direction. Or if you want, in the Lorentzian point of view, they are non-relativistic. Time and space are treated differently. And what is the formalism I'm going to use to study these fixed points? It's going to be Zamolodchikov's conformal perturbation theory. That's why Lifshitz is going to meet Zamolodchikov. So let me start with a concrete motivation. So sometimes you think about CFTs as fixed points of continuum quantum field theories, but very often it's good to see them as the fixed points of lattice models in the thermodynamic limit. And by lattice models, we can mean one of two things. We can mean Euclidean statistical mechanics, equilibrium at some temperature, where the number of dimensions is just the number of spatial dimensions, and we have some lattice, and we have some classical Hamiltonian that depends on some classical variables. But we can also mean the quantum phase transitions in quantum many-body systems, where we have some Hilbert space and some quantum Hamiltonian, and now Hamiltonian involves us in time, so there's one direction which is time-like. And okay, we think about maybe some spatial Hilbert space with some spins, and time is treated very differently. It's treated in the continuum, and there's some quantum Hamiltonian. And then we find critical points, either at finite temperature here or at zero temperature. And what is known for many decades is that critical points exhibit some scaling symmetry. They also often exhibit conformal symmetry, but this is a subtlety that I don't want to discuss. But scaling symmetry is, of course, a mandatory feature. And often, we almost take it for free. Euclidean systems come along with rotations, and Lorentzian systems. I'll refer to quantum many-body systems as Lorentzian, even though it's a bit abusive, have Lorentz symmetry. And the question I want to ask is this natural? Is this is appearance of continuum rotations and Lorentz symmetries natural in the normalization group sense? And a very naive person, such as myself, would say the following. Well, if you're in a Euclidean lattice, you look from very far away, discrete rotations look like continuous rotations, discrete translations look like continuous translations. It's obvious. I mean, of course, there's going to be rotational symmetry. So this is a naive answer to this question. Instead, for quantum many-body systems, it looks like a miracle if you're naive. You start with some discrete space and some continuous time, and you somehow expect that the relation between time and space is linear, like in Lorentz invariant quantum field theories. This looks like a miracle if you're a naive person. So what's the correct answer? What is the opposite of naive? The opposite of naive is Wilsonian. And the Wilsonian answer is very simple. It's natural to have these symmetries if, and only if, there are no relevant operators that break these symmetries. rotations or Lorentz. Of course, there is a small modification, which is, okay, maybe there are such operators, but I am smart enough in my lattice Hamiltonian not to turn them on, which very often happens in Euclidean lattices. But it's much more complicated to do at the level of quantum Hamiltonians.
This should be the stress tensor, right?
We will discuss, the stress tensor is kind of a special case. I'll talk about it later.
Okay,
we will make this precise very soon. This is just very broad. And okay, before telling you details about Lifshitz theories, because it's not so standard in our community, I should say, for honesty, that my real motivation for working on this was actually a question that João Penedones asked me, which is, so I won't write, this is motivation, this is the honest motivation. If you start with a CFT in the UV and you flow to a CFT in the IR, but in the intermediate scales of the flow you break rotational invariance, is it true or not that the theorem holds? So this is actually the question that got me into this topic. I wanted to give João credit for making me think about this. So okay, now let me review what is known about these fixed points that do not preserve rotations or boosts, Lorentz boosts. So review. The first thing is the definition. What is a Lifshitz fixed point? It's a fixed point where there's some special direction. I'll call it x0. It could be Euclidean, some Euclidean direction or time, and some spatial directions that touch the critical point, satisfy some scaling law, where there is a privileged direction that scales with a power that is not 1, and the rest of the directions scale linearly. And so if this happens, we say that the system has Lifshitz symmetry with dynamical critical exponent, and this is the key object in Lifshitz theories, dynamical, so let me write it because it's an important observable exponent, Z. So this is, even before talking about a Lifshitz theory, what are its observables, what are the things we want to compute, we need to identify them into some class, which is how this privileged direction scales with respect to the other one. What are some consequences of this? So since I started with a lattice motivation, let me say that if we are on a lattice at finite volume, L, and we look at the way that the gap vanishes, so the difference between the ground state and the first excited state, we're used to that in CFTs. The state operator correspondence tells us that these are proportional to the scaling dimensions over L. This is just the state operator correspondence. But now in a Lifshitz theory, we'll find a correction to this behavior controlled by this exponent. So of course I didn't say it, it's obvious. So Z equals to 1 is just our usual rotational invariant or Lorentz invariant CFTs. So now we have this different behavior, and this is a very nice test if you're doing the MRG, like me and Jun Chen, to find out if your theory is an actual CFT or it could be some critical system that's non-relativistic. But we are bootstrappers. We work with correlators in the continuum. So let me tell you something about that. What do correlators look like in these theories? So let me start with a two-point function. Okay, let me write time instead of x0 just to make it easier for me to have some notation. What do two-point functions look like? So rotations are broken. There's no sense in talking about spin of the operator. So let's just, all operators are quote-unquote scalar.
Why do you say that the rotations are broken? You would still have spatial rotation.
Thanks. Very good. There could be a spin inside this. I'm in my mind, thank you for mentioning that. I'm going to be working 1 + 1 dimensions, so I won't have that. But thanks a lot, indeed. So time is privileged. There is some power law in time. There is some scaling dimension, as you would like usually. But now, since time is the privileged direction that scales with Z, you should put the power Z here. And then there is some quantity that you can build out of 2 points. Let me not use phi, because I'll use phi later. Let me use capital F. That is still invariant under this Lifshitz symmetry, which is simply a ratio of the time distance to the space distance. This quantity is obviously Lifshitz invariant, so 2-point functions are highly non-trivial. They're very far from being fixed.
Sorry, is Z an independent?
Is Z an independent label of these operators, or is the same for all
Z
operators?
is the same for every, it's a property of the theory, not of the operators, right? The theory scales like this, so every operator has some correlation function. It's labeled by delta O, like we are used to, but Z plays a role in the structure of the correlation function. So now I should say that a lot of the literature on Lifshitz theories specializes to a very interesting case, which is the case Z equals 2, which is often called Schrödinger symmetry. Why? Because it's the symmetry of the Schrödinger equation. The Schrödinger equation is second order in space and first order in time. So it has this scaling invariance where we scale time twice as much as we scale space, right? And in this case, there are rather remarkable results by several people. Some important names are Damson and Malte Henkel, for example, but I don't know this literature in completely broadly. So I apologize to important people I missed. The correlation function here, the power law, is as predicted. Z is 2, so we'll just write T to the delta O. But then this non-trivial function can actually be completely determined because there are additional symmetries other than just these scalings. There are Galilean boosts. So this is some version of the Lorentz transformation, non-relativistic. And in fact, there is some non-relativistic version of special conformal transformations. This form the so-called Schrödinger algebra. And what it allows us to do is to completely fix this function. It has some very interesting form. It's some Gaussian in space with some width that is modulated by time. And there is actually some constant here that is called the Galilean mass. The reason why there's an additional number here is because this Schrödinger algebra has some center, and this center it's a number that we associate to the representations, and it's some Galilean mass that is invariant under Galilean boosts. So to every operator, there is this hidden quote-unquote quantum number that determines the two-point functions. So that's very nice. But already at the level of three-point functions, things are not completely determined. So it is, there are more restrictions than in generic case, but it's certainly harder to study these theories than our beloved relativistic CFTs. So now, what do I want to say? What are examples of these models? Where do they appear concretely? Just to, give some idea of what we can study with this.
Sorry, are you saying these Galilean boosts and the special conformal transformations, they're only there for Z equals 2,
yes,
but more in general?
That's exactly what I'm saying. Z equals 2 is special. Only for this case, there are additional symmetries that enhance this Lifshitz scaling, and they are strong enough to fix the two-point function, not for general Z. Malte Henkel has some arguments for Z equals 2 over n, where you can also fix the two-point function. OK, so now, just to make things a bit more concrete, let me give an example of a free theory of this symmetry, which is the free Lifshitz scalar. What does it look like? It's just a free scalar. The kinetic term in time is as we like. Then there's some free coefficient, because there's no relation, no direct rotation between time and space. And we have some spatial derivative to the power z. It's obvious that this theory has some scaling symmetry where time and space scale differently. And in particular, this free Lifshitz theory actually describes some interesting quantum phase transitions. So for z equals 2 in 2 plus 1d, this free field is the quantum critical point of some quantum dimer models. If you don't know what it is, please ask me afterwards. Just to say that it's some interesting quantum condensed matter model.
Sorry, Antonio, can you comment maybe what? So I get that z equals 2 is cool because it has like this amazing symmetries and so on. But can you explain why, z was some critical exponent to begin with, right? And
yes.
So I would expect it to be like, I don't know, 2.013, and why would I ever expect it to be 2?
Very good. Again, there's the naive answer, there's the Wilsonian answer. Let's go directly for that. If your action preserves such things, you would expect it to be 2. And maybe it's not so hard to write actions, especially in quantum mechanics, that preserve Galilean boosts. So I would guess there are many actions that are Galilean boost invariant, and z equals 2 appears very often. But there are many other theories where z is 1.5 or 1.86 or whatever you want. So that's true. But this is some type of a privileged situation that happens more. Also, z equals 1 happens many times, as you know.
Yes, right, but
The thing is that you first look at all Brazilian fixed points, and then some of them will have 2. And
Yeah.
if your fixed point have 2, it's nature from their G point of view.
Yes.
So there's going to be a finite fraction which has exactly 2, finite fraction which has z exactly 1.
Yes.
And the other ones will have z whatever.
Yeah. Some random.
It's not so often the mean field theory.
Sorry?
Z equal 2 is often the mean field theory.
It's often the mean field theory answer if you assume the symmetry from the beginning, right? If I put here 2, well, then z equals 2 is the mean field theory answer. But you can start from the beginning with a generic z. This is a Gaussian axion with z generic. So nothing stops me from studying. Yeah. Okay. Yeah. So, okay. There is some privilege to local actions with integer z. Thanks. Okay, let me, I'm going to go to my model, but let me just briefly say how general these things are. So they appeared in both Hubbard models in superfluid trivial phase transitions. They appear in all sorts of fermion models, like even graphene. If you try to model the Coulombic interaction, you know, there's a Fermi velocity, and there's C for the electromagnetic interaction. Of course, that breaks relativistic symmetry. So there are plenty of interesting things to study. And a lot of them, and this is the key point here, in the literature, what people do, the main strategy is they start in the UV with some Gaussian theory of this type, maybe with fermions, maybe with different z's. UV is Gaussian, z not equal to 1. And then people deform and find some interacting Lifshitz point. So that's the standard approach in the literature. What I'm going to defend today is a different approach. I'm not the first person to use it, but it's far less used. So
in this main strategy, does that change along the flow?
it can change along the flow. It can change along the flow. Thanks. Certainly the speed of light can change along the flow. The speed of sound can change along the flow. Also z, I think, can change along the flow. Depending on the interactions, depending on what you allow, right? If this is the only non-local thing and z is non-integer, maybe it's fixed. But for integer z, I think it can change along the flow, depending.
Because there's a response nomination for the first term, and the key comes in.
I see.
Like from that action you can get any z, but in actual models you actually get arbitrary large.
Again, Slava's argument is more or less correct. Z equals 1 and z equals 2 happen with some finite frequency, and other values of z you can find in different models as well. I'll give some examples.
But I meant like, that can be arbitrarily large, like, or do you actually find mostly values that are, I don't know, order 1?
You can cook up models where z is arbitrarily large, but with some degree of naturality, z is typically between 1, 2, not so large. But you can cook up models that are arbitrarily anisotropic. Yeah, you can just send this stuff. Yeah. Good. So now let me tell you my approach, which is you start from a CFT in the UV. We like it, and we break Lorentz symmetry by adding a relevant spin 1 operator. So dimension of V is smaller than D. Why is it enough to consider spin 1 operators? Because by unitarity bounds, operators with spin greater than 2 are always irrelevant, so that's great. The stress tensor is marginal, so this is what John Chen was anticipating. But the stress tensor, we know what adding the stress tensor to the action does. It's changing the metric. The stress tensor captures the variation of the metric. So adding the stress tensor is kind of a redundant operation. You can just redefine the metric in the original theory. So it's not really a physical RG flow. So then what we are left with is spin 1 operators. So there is no Pandora's box. We just add one more class of relevant operators that we need to worry about. So I think this is why this is a kind of a more systematic approach, because we just need to classify a second set of operators.
But if you're talking about statistical mechanics, I mean, if Lorentz symmetry is not sacred, then I would think unitarity is also not sacred.
Fair enough, but there is still a large class of Lifshitz models that are unitary that you can study this way. All of the ones I listed, the examples, are all unitary. The thing I will write, okay. Unitarity is kind of more natural from the Lorentzian point of view than the Euclidean point of view here. We'll see that in a second, but the space of models that can be studied this way is still very interesting. Let's put it that way. Okay, so this is our plan. instead of starting with some Gaussian theory with z equals to 2, we start with some Gaussian theory z equals to 1. We break Lorentz symmetry, and we flow to some z at the Lifshitz fixed point. And now I will present a model where this can be done in a controlled way using conformal perturbation theory, which is, as far as I understand, did not appear in the literature before. I should comment that Cardy studied the Potts model, deformed by the spin 1 operator of the Potts model, but this operator is not weakly relevant. So he gave some Cardy magic argument to conclude what the Lifshitz theory is. And there, so let me comment Cardy, Carol Potts. There he finds a theory with z equals 1.5, so it doesn't have to be an integer. Huh? OK, so now let's go to the model I cooked up. Let me call it the Lifshitz-Zamolodchikov model. We start with two p minimal models. If you know me, you won't be surprised. You send p to infinity, which is the regime where c goes to 1 minus things of order 1 over p cubed, squared. So it's the accumulation point limit of the minimal models. We take two of them. Why do we take two of them? Because for one of them, there is no relevant spin 1 operator that's not a descendant. The relevant spin 1 operators are descendants, and descendants don't modify the action because they're total derivatives. So we need to cook up some primaries. And for that, we take two minimal models and write the following spin 1 operator. Phi12 d mu phi12, where phi12 is some operator whose dimension approaches 1/2 at large p. We take it in one of the copies, take a derivative of the phi12 on the different copy. So this has spin 1, obviously, and dimension that is close to 2. So the dimension of this guy here, of this vector operator, is 2 minus 3 over m plus order 1 over m squared. So it's weakly relevant. It's good for the epsilon expansion. M is p. It's my, yeah. They forced me to change because my m is weird. OK. It turns out that if you start running the perturbative RG, you don't turn on just this vector coupling. For consistency, you need to also add a scalar coupling, which is here. There are no derivatives. This is a good old-fashioned scalar deformation of the type Zamolodchikov used to flow between minimal models. So this is the one that is most famous. And the dimension of this operator is also weakly relevant. It's 2 minus 4 over p plus order 1 over p squared. So now we can run the RG machinery. Conformal perturbation theory tells us that we can compute the beta functions for these couplings by studying the OPE of these weakly almost marginal operators. And we need to be a bit careful because the standard derivations in conformal perturbation theory involve integrals with scalar operators, and now we have spin. So there are some extra angular dependence that will modify the conformal perturbation theory formulas. But you know, you do your homework, and you can derive the beta function equations. And here's what they look like. So I'm going to be picking holomorphic and anti-holomorphic components for this vector. So G mu has two components. I'm in 1 plus 1 dimensions. So I will have GZ and GZ bar. And I can compute independently the beta function for each one of them, and then also for epsilon. And the results is as follows. This is the classical piece from dimensional analysis. And then the one-loop results involve, as you know, OPE coefficients, which I'll write as ZZ epsilon. So this is two V's, two vectors and one scalar. It's the OPE coefficient that you get by computing it. The same thing happens here. It's the same OPE coefficient. And then finally, for the scalar deformation, there are two contributions. One from the ZZ epsilon OPE, which is again the same OPE coefficient. And there's a second OPE coefficient here that comes from epsilon having a non-trivial OPE with itself. Epsilon is this phi13 operator. So OK, we have a three-dimensional RG space. We can look for the fixed points. We can set the three beta functions to 0. And what do we find?
Is it important for you that this G, this coupling vector G, is it going to point in some Euclidean direction or some Lorentz direction?
Very good. I'm starting from the Euclidean direction. It's just to make things easier. In the end, we can rotate and think about it. In practice, I did the computations Euclidean. And yeah.
But OK, if you do it in the Lorentzian, I would prefer if you stayed always in Euclidean, but maybe you won't find a fixed point then.
No, I find a fixed point in Euclidean, yeah. I will, let's stick to Euclidean, and
So
then I'll just say some words about Lorentz.
So then there is just like, I could just rotate this vector G mu in, say, direction 1 and talk about just a single coupling
That's
G1?
right. We're going to see that.
Okay.
Yeah. So indeed, the Slava is anticipating. There's no reason to pick a preferred direction, but it's nice to keep them all for the following reason. We can pick the two components, GZ, GZ bar, and the scalar coupling. We start in the UV with two decoupled minimal models. And as you can see, it's consistent in these equations to set to 0 all the vector couplings and just study the epsilon deformation on its own. This is what Zamolodchikov did. So certainly we will find some fixed point, which are two minimal models where the p goes to p minus 1. What is interesting is that there is a circle of fixed points, and this is kind of obvious, as Slava is saying. If I find a fixed point in one direction, well, I just chose the direction.
Why do you plot the two decoupled minimal models at non-zero value of G epsilon?
It's 0. It's just nicer to draw, but this is 0 here.
Oh, okay.
Sorry. And this is and the arrow points down. It just looks. You will see why. Okay, let me not put axis. So this is 0, of course. Why it looks nice is because there is some circle here of Lifshitz fixed points, and of course, as Slava is anticipating, they are all the same. If I point in the z direction, I can point in the x direction, in the z bar direction. Doesn't matter. But let me call this a Lifshitz circle of fixed points, because it is. You can pick any value and you get the same theory. So what happens as we diagonalize the dilatation operator on the circle of fixed points, which are all equivalent again? We just do the standard RG thing. There are going to be 3 eigenvalues, and what we find? One eigenvalue is 0. One eigenvalue is plus 2 square root 2 of m. Let me call it gamma 1, gamma 2, gamma 3, minus 2 square root 3 over m. So there are a few obvious things that we can see. First one, all the 3 eigenvalues are different, which means that rotational symmetry was broken, because we started with a vector, and the two components must have the same anomalous dimension, and the scalar can have different. So there should be a double degeneracy if there was rotational symmetry. That isn't. So rotational symmetry is broken. That's obvious. Rotational symmetry, boom, gone. The second thing we see is that there is a marginal operator. And the marginal operator is what Slava is anticipating. If I pick a direction in the UV like z, I could have picked z plus a little bit. And this is exactly the same fixed point, really. So this is some marginal operator that, if Filina was here, she would definitely come up with a nice name for this operator, but I'm not so creative, so let's call it the frame operator. That just tells you along which direction you broke rotational symmetry. And finally, and this is actually quite interesting, there are eigenvalues which are positive and eigenvalues which are negative, which means that the Lifshitz fixed point is not stable. Even though it is the fixed point of least symmetry, it's not the stable fixed point. So the RG diagram kind of looks like this. If we tune, we can hit the Lifshitz phase. And of course, from the Lifshitz phase, we can flow to the decoupled minimal models. But if we don't tune, we will just land back on the Lorentz invariant fixed point. So in this system, Lorentz symmetry is emergent. I can break it in the UV, and somehow I always restore rotational symmetry in the infrared. So this is precisely agrees with the conditions of the problem that João proposed. And in this particular case, we see that the C theorem is still satisfied, even though we broke rotational invariance. But I should say that there are many examples studied in the literature on this, and I think it's the case that the C theorem is not satisfied in general in this scenario, but okay. For this particular model, it is.
Are you sure that this marginal operator is actually there, and which is marginal?
Yeah, you really find the eigenoperator. It's just the angular component of the vector in polar coordinates, and it amounts to picking in which direction you broke the rotational symmetry.
Yeah, but there are some situations when you find 0 eigenvalues from beta functions.
Yeah.
But because the actual operator is a total derivative, the 0 eigenvalue doesn't tell you anything. It's just a redundant operator. For example, in this situation, there has to be some operator eaten by some component of the stress tensor. And I don't know, you didn't say anything about the stress tensor, but presumably it's going to pick up some anomalous dimensions, so it should eat someone. And so this operator could be actually a descendant of stress tensor, and it's not marginal at all.
I'm pretty sure this operator is marginal, but it's marginal in a trivial way. in the same way that if you take, say, a conformal defect and you break a global symmetry, there's this marginal operator, this tilt operator that they talk about.
Okay.
It's really a choice of frame. So it's a conformal manifold of identical points.
No, but in some cases, when you, for example, break global symmetry to a discrete subgroup, and you do beta functions, you will find naively when you find a fixed point, you diagonalize the Jacobian, you will find 0 eigenvalues. And then you say, oh, well, there are some marginal directions, and then maybe you'll rotate the frame. But in that case, it's just bogus. There are no marginal
But
operators.
this guy cannot be a descendant of the stress tensor, right? Because it has dimension 2 in spin 1. So I don't think there is no candidate for that.
Okay.
But your stress tensor doesn't have to be symmetric anymore, right?
That's right.
So
that is correct.
It's it could. I think it would be the antisymmetric part of the stress tensor. So it's not a derivative, but it's like it will appear in the divergence of the rotation current.
Okay, I have to admit I didn't explore this subtlety, but I'm pretty confident from the physics that it's exactly marginal, because I mean you can pick any frame you like.
No, but the point is that the two theories that you're considering
Yes.
are identical theories.
Yes.
So sometimes if you have theory 1 and theory 2, they are identical.
Yes.
You say, oh, well, there is an operator which rotates the theory 1 to theory 2, but because the theories are identical, this operator is not forced to exist. In some cases, you know, if there is a teal,
Right.
then it actually exists, but in other cases, like it's a global symmetry broken to discrete subgroup, then
It's really gone.
Okay.
Okay. It's work in progress. I'll try to figure this out before I
mean,
write
the difference with tilts is that in tilts you still have the bulk, and you can compare different ways of breaking the symmetry. You can have two defects in the same bulk, and you can see that they break different subgroups. Here it's not less obvious. I mean, maybe it still works, but it is well known.
I have no claim that this is non-perturbatively marginal, but it is marginal at one loop, and okay, that's my statement.
It has to be at all loops marginal, because there is always going to be, because of symmetry, a circle of fixed points. It's not going to break down into self-fixed points. And you can just study, say, in 4 minus epsilon, multiscalar theories. You can find a fixed point which is not like ON symmetric, but some discrete subgroup.
Yes.
There is also going to be in the, there are many couplings. There's going to be some kind of manifold of fixed points.
Yes.
And it's going to have zero eigenvalues exactly to all orbiters, but there are no marginal operators in these theories.
I see.
So you have to be careful when you're making this.
Okay, we need to, the obvious thing, it's that it's not a derivative of stress tensor, but maybe it is some antisymmetric component, as you say. I don't know the answer. I will think about it.
Yeah, but I had another question. So you were talking about this dynamical scaling exponent Z.
Yeah, I'll compute it. I'll tell you what it is.
Yeah, but so what I'm slightly confused by, right, is that you go through the, presumably, I don't know, maybe you can correct, you go through this usual procedure, introduce some scale, mu, blah, 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 you compute some d log mu, whatever. But doesn't that, so the beta functions that you're computing and the transformation for which you find the fixed point, doesn't that by your construction just scale the space and time homogeneously? Because of how you start?
But Z will also be only corrected at one loop. So doing that is a second loop effect that I don't need to worry about when I find a one loop fixed point, right?
I see. But if you were to go to higher orders, then somehow you need to...
Then I need to rescale the components according to the Z that I found in the previous order perturbation theory to do it consistently.
I see.
But let me tell you what Z is. Oh, I'm over time.
But at the more technical level, you could say, okay, my theory also has another marginal operator. The more technical level, say, okay, my theory actually has another marginal operator, which is the stress tensor.
Yes.
And since you're breaking rotation symmetry, why are you not adding stress tensor to the action with some coefficients and also renormalize those terms?
I probably should, but I could I not still absorb it as a change?
Well, the point is that at every RG step, you would find that those coefficients would be a little bit renormalized. Then you would have to reabsorb them. It is actually one of the ways to compute the Z exponent. But you are saying that somehow that thing, you seem to be implying that that thing would not affect this.
I think it will not affect, because you can also independently compute the Z exponent, and this is the last thing I wanted to say anyway, by checking how the symmetry of the stress tensor is broken. And it's broken precisely by order 1 over m. The conclusion, it's 1 minus 6 over m. And you can, this is how Cardi does it in his paper. He just reads off the Lifshitz exponent from the breaking of symmetry of the stress tensor. You can do some arguments with rescalings, and this will be the conclusion. So the point here is that, Z is broken perturbatively, and I think you are right that at the next order in perturbation theory, I should take this into account, include the correction of the stress tensor, and so on. But I think this is consistent at one loop order. So of course, Z is this plus, I should write, plus order 1 over m squared. And at that stage, I should start being careful. But I think at one loop order, I'm safe.
It's just a question of whether stress tensor appears in the OPs of this guy.
It does not. It does not.
Yeah, then it doesn't appear.
It doesn't matter, yeah. It does not.
If it doesn't appear, then why would Z be renormalized?
No, because it's because of this. Because now you don't have proper scaling symmetry.
Yeah, but what generated this effect? If I do the computation adding the stress tensor to the action, what I should see is that once I do the RG step, some components of the stress tensor are rescaled differently.
Good.
And this can only happen if they are generated.
I could see that by adding the stress tensor to the action, but the OPEs don't generate the stress tensor, so I can do things in 2 steps. I mean, this is a closed.
Of course, they will generate.
The next operator here, so they generate the stress tensor. What is true is that if you add the stress tensor, the coupling to the stress tensor is not going to appear at this order in this beta function.
Yes.
So you can consider this as closed. So this is correct.
Yes.
In order to write the beta function for the stress tensor couplings, they would actually receive these contributions. At least like GZ bar would appear.
Yeah, I think it will.
But then you don't need this to find the fixed point.
I don't need to find the fixed point, and then I can read off Z independently by the breaking of the symmetry of the stress tensor. So I'm pretty confident that this is the correct result.
Maybe an analogy. In the non-Lifshitz case. Yeah, as you know very well, to find how the central charge changes between the UV and the IR, a one-loop calculation, as far as the beta functions are concerned, will tell you what that is to 3 loops.
Yes. Thanks, Connor. Okay, just to finish, this thing, needs to be cleaned up. I wrote work in progress. I was in the afternoon, so don't shit talk me too much. This needs to be cleaned up. There's an interesting version of this in the 4 minus epsilon expansion. You can write down weakly relevant vectors in the ON model and play around with that. And also, finally, Z equals 2 case is extremely restrictive. It has a lot of symmetry, and we haven't thought about bootstrapping those theories, at least not seriously. And I think it might be worth it. So that's it. Thanks.
Just a very quick question. Does it make sense to play this game in 4 minus epsilon, since you also have marginally...
Yeah, that's what I said 12 seconds ago.
Okay.
So you take the ON model, you take your favorite phi I, phi j, phi k, phi l, and now there's a spin 1 operator. It won't be there in every representation.
Yeah.
It will be in some special representation, but this guy has dimension 4 minus epsilon and spin 1. So yes, you can... Maybe when epsilon goes to 1, it describes some interesting phase transition. I don't know. Johan, I think, told me that operators here are either vectors of ON or in this representation. So you're going to break some amount of global symmetry anyway when you do this. But OK, you can do it.
Yeah, so I have one comment / question. So in more than 2 dimensions, something very similar to what you're describing has been done, which is the fact that, well, if you want to, you can think of these vectors. For instance, if you take this vector as a conserved current, the deformation you're doing is putting the theory at finite density.
Yes.
Okay, so this has been studied in a lot of examples.
Yes.
But what happens usually in higher dimensions is that once you put the theory at finite density, if you are starting from a bosonic theory, you end up in a phase that is breaking, which is spontaneous symmetry breaking.
Yes.
So it's a superfluid phase.
Yes.
And then you don't float with CFT, but you float with gapless phase.
Yes.
Okay, so now, first of all, it's not clear why this is disallowed in 2 dimensions, because you're breaking Lorentz invariant, you're breaking space-time symmetries. So Coleman's theorem no longer applies, because that relies on space, on Lorentz invariance or on Euclidean invariance if you're in Euclidean. So first of all, the first question is it possible that in 2 dimensions you flow to a gapless phase or not? And then the second question is like, do you know? Sorry?
To which gapless phase?
I don't know. That's the question. Yeah, no, but to a non-scale invariant gapless phase.
You're saying when I add the conserved current specifically, that's your question?
Yes.
Yes, I think so, yeah. I think take the compact boson, couple it to the spin 1 current, you go to finite density.
Yeah, exactly. Has that been done? If yes, was that?
I haven't seen it, but I'm sure it's been done. And it's going to be some gapless.
If you know the reference, I'll be interested in looking at it.
Yeah, I'll try to find the reference.
And yeah, in more than 4 dimensions, then the question is, what's your suggestion? Because in more than 2 dimensions, you actually flow to a gapless phase, to a symmetry breaking phase. So what will be your what will be interested in doing in more than 2 dimensions?
I'm just saying that there's since there is so much data known about the ON model, there are relevant vectors that, okay, break the global symmetry down to some discrete subgroup, but presumably they will have fixed points in the epsilon expansion where the Lifshitz exponent is not 1, but it's 1 plus order.
No, but if you float, you get the superfluid EFT.
No, this is not conserved operator. This has dimension 4.
Okay, okay,
Yeah.
okay, I understand. Thanks.
So what happens is that because the conserved current, that you mentioned d-1, so that RG flow is more violent, so
yeah,
it leads to a gapped phase or gapless phase. But well, this RG flow is kind of gentle.
Yeah. I should say that controlled studies of the Lifshitz exponent were also done by Son in the limit of large flavor number. So we took non-relativistic fermions, large flavors, Coulomb interaction, which treated as instantaneous. He was able to also compute find a critical point and compute it in the 1 over NF expansion. But that, some different approach, different model, whatever. Similar logic where it's a gentle RG flow.
I don't understand how you're hoping to study this operator.
Sorry, it is dimension approximately 4. Okay.
Yeah.
Okay, ignore me. That's fine. I thought that phi has dimension 1/2.
No, I think for tricritical leasing, this should definitely work. I think so, yeah. So question is adding a spin 1 operator that carries momentum on the lattice and see what happens, yeah?
Yeah, we're going to get to the next talk.
Yeah, sorry.